Okay, it's time. It's 10 past 10, so let's settle down and welcome Patrycja, who's going to talk to us about JWT security.
Okay. Hello, everyone. It's nice to see so much interest in security. Today, I'm going to tell you about JSON Web Token security. How many of you uses JSON Web Tokens? Yeah, almost all of you. Yeah, that might be an interesting talk to you. So first, briefly about myself. I've been doing professional software development for over 20 years. I've always been close to code, and I still am. And I must say, I love it. My interests focus on patterns and anti-patterns in software, along with the ways how to improve software quality. I work on automated tools to detect and refactor various software defects, like security vulnerabilities, like performance anti-patterns, like database issues. So basically, security vulnerabilities are my daily job. What am I gonna talk today? First, a brief introduction to JSON Web Tokens, just for all of us to be on the same page and to use the same terminology and have the basic knowledge. The key part of today's talk involves 4 demos that reveal some security problems when it comes to the specification, the implementation of tokens libraries, and some problems with our applications. There are a number of caveats when it comes to JSON Web Tokens, and we will start with the first very difficult thing, which is how do we actually pronounce it? Because as a native Polish speaker, I usually pronounce it as JWT. In English, I've heard many times JWT, but when you take a look at the RFC, the suggested pronunciation of JSON Web Token acronym is the same as the English word JWT. So JWT means the smallest bit, iota, or to JWT means like to write briefly something in an informal way. So both those things are somehow connected to JSON Web Tokens. So I think I will stick with JWT pronunciation as it's the most popular, I think. What do you think? Is that fine for you? Great. So when we've already opened the RFC, let's take a look at the definition. It's quite lengthy. To cut it short, we usually use JWT to represent a self-contained session of an authenticated user and usually his or her roles. It's a set of claims that are encoded and digitally signed. It's always handy to take a look at the example. We see that a JSON Web Tokens is a long string consisting mostly of letters and numbers. When we take a closer look, we can recognize 3 parts separated by dots. These 3 parts are a header, a payload, and a signature. And each part is base 64 URL encoded. When we decode these 3 parts, we see that the header and the payload are just JSON objects. So here we have the first problem with JWTs, lack of confidentiality. So we shouldn't store in claims any potentially confidential information because it's just a plain text. Base 64 URL is not encryption, it's just encoding. So everyone can easily decode it. So in this case, the payload, you see that a header contains an algorithm used to generate a signature. And then a payload consists of a set of claims. In this case, we have 4 claims: the subject, issued at, issuer, and expiration. Those are not mandatory. You can use your own claims, whatever you want. And the signature depends on the algorithm. It's just digitally signed concatenation of a header and a payload. And here is an example how we can actually use JSON Web Token in our HTTP request. Usually, JWTs are passed through to the server via authorization header, but that's not the only or mandatory means. We can pass the tokens whatever way we like. So in another header, in URL parameter, or probably the least popular way in a cookie. So that's all when it comes to that theoretical foundation. Now let's move to the demo. And the first one involves the non-algorithm. Probably only a few of you knows that the spec supports non-algorithm. Non-algorithm means that there is no algorithm, basically no signature. And now I will show you how we can use this property of the spec plus some implementation problems in the library part. So I've prepared a demo. It's available, and I will need your engagement as well. So now switching to my demo. It's available at http://yonlabs.com, and I have a question for you, just to register as new user, because I'm gonna hijack today your sessions, so we need some sort of an application. This is this vulnerable application. Please go to, I will post this link on my Twitter account, which is YonLabs. And please go to this link. Use a nickname, don't provide your real passwords. Just in case, reminder. And I'm logging in. I'm already registered. OK, so there are a couple of you. We will wait for much more users. OK, don't be shy. Register. OK, we have. OK, you are fast. We see that this application is protected by JWT. We can see this in session storage. We have a token. This is such a long token. Let's take a look how the details of this token look like. So it's a token. I'm using JWT.io page. It's a very useful online tool to encode and decode JSON Web Tokens. So I copied a token from my session storage, and we see that this token is protected with HS256 algorithm, which stands for HMAC with SHA-256. And we have a set of claims. Subject usually represents a user, authenticated user. We have issued at, issuer, expiration date, etc. So I've prepared, now what I'm gonna do. I've prepared a token which is which uses non-algorithm, and in subject claim it's a user ID 7. So we can take a look at JWT IO page. We see that the algorithm is known, and the structure of the claims is the same, very similar to the original token. I've only changed the subject. And now I will use this token and just replace my token with this non-token and refresh the page. Okay, Ellen, you've been hijacked. Where are you, Ellen? Okay, congratulations, you are the first person to be hijacked. So you see that even though the original token was protected with digital signatures, we managed to prepare a token with non-algorithm, which was accepted by the server. Why? I will explain that to you in a moment. You've seen that already, that there is no signature for non-algorithm. And the problem is in the spec, which requires non-algorithm. And the problem is also with IO JSON Web Token library. Because this is the code used for verification. It looks pretty fine, right? We have we are setting signing key as secret key. We are doing parsing. Then we are getting claims and subject from claims. So it looks perfectly fine. However, the problem is here because we've used parse method, which does not verify the existence of a signature. It's like the code. If we used parse claims JWS, that would verify that there is no signature and raise an exception. So this is a very subtle error, right? And this IO JSON Web Token library, it's not the only library with the none problem. When we take a look at the National Vulnerability Database, we can find many more issues related to JSON Web Tokens. One of those issues reveals that the non-problem was existent in another library as well, albeit much less popular. And check out the year of the entry. It's 2018, so the issues, so only like 2 years ago. How many applications are not patched yet? Who knows? So I'm not sure what was the rationale behind the decision to support non-algorithm. I suspect it was kind of premature optimizations. Non-algorithm was supposed to use behind the authentication wall inside, for example, a farm of servers to speed up authentications, because verification of digital signature takes time. Not so much time, but still it takes some time. So getting rid of that verification could slightly improve the performance. But for me, from the security point of view, it's definitely premature optimization. Also, that demo revealed another problem, implementation problem, with libraries and their APIs. They are not very clear, right? Also, it leads to another problem that we as developers, we have much more issues because we have to very, very well and in details know our tools. So this is that example with Parse versus Parse claims JWS. In another library, it's a dichotomy between the code versus verify. So best practices include understand what you are doing. Yeah, you must think. It's worthwhile looking at a national vulnerability database to check out whether your library has any issues. And if it's always a good approach to use the latest release. Also, from the implementation point of view, as developers during the verification phase, we should require a specific algorithm and a specific key. Why to require a specific algorithm and a key? Because there are other problems with JWTs, like this vulnerability entry raised in 2016, where basically the base idea is to trick a server to use RSA public key as an HMAC secret. So basically we have a server. The scenario could look like this. We have a server which supports JWTs with RSA and SHA. So basically during generation the server signs a JWT with a server private key, and during verification it verifies whether a signature is correct using public key. So this is a regular scenario, and let's take a look at a hacker which wants to abuse and exploit our system. So hacker prepares his own token, changes algorithm to HMAC plus SHA, and it often happens that public RSA keys are publicly available. We protect our private keys, but public keys are not that well protected sometimes, or even sometimes they are published somewhere on the web. So let's assume that this was the case. The public key was available to a hacker. So a hacker changed the algorithm to HMAC, which is a symmetric algorithm. It uses a secret key. And hacker used this RSA public key as a secret for HMAC. What happened? Server accepted this token because server decided that it should use HMAC plus SHA, and the server has had this RSA public key configured in its configuration, so it used it as a key, but not for RSA, but for HMAC. So this way, it was a successful verification, and a hacker could exploit this issue. That's why we need to require, during the verification phase, a specific algorithm and a specific key. Another example is connected to another issue raised in 2018. Basically, the vulnerability allowed a hacker to provide a public key for verification in a token header. So, as you see, the vulnerability was due to Node, the library, following the JSON Web Token specification. So, because it followed the specification, there was a serious vulnerability in code. The standard specified that the JSON web key, representing a public key, can be embedded within the header. And how this thing could be exploited? That was pretty easy. Again, the same situation. We have a server with RSA with SHA. And a hacker prepares a token which is RSA signed, but the hacker signs it with his own private key and provides public key for verification in the header. So if a server accepts this key, doesn't require that this must be the server configuration, then we end up with a successful verification. So that's why it's so important to require a specific algorithm and a specific key configured on the server side, not provided by a user. But here is something more optimistic, the library with a nice API design supporting security. Please note how strong typing and object-oriented programming help to achieve good security. We have an abstract algorithm class with several subclasses, and a key and an algorithm are packed together, so no problem with a different interpretation of a key, like in that case of RSA key used as an HMAC secret key. So this is a nice example and a good example for us as developers, because we quite often see programming to primitives like integers and strings. I often call it string-oriented programming. And it usually leads to a lot of if-then-else and quite messy code, and messy code is a primary source of security vulnerabilities. Plus with messy code, those vulnerabilities are pretty hard to fix. Okay, so now let's move to another demo. It will be about password, or more like key cracking. I will log in again. And this is the token. We know this is HS256 algorithm. And I have GPU instance or virtual machine with 4 GPUs. And I will use a tool called Hashcat. It's a password cracker, or I'm sorry, they call themselves password recovery tool. So I will use this password recovery tool for JSON Web Token cracking, and you will see how simple that is. So basically, I have a simple script. Right. Maybe this will be better visible for you. Basically, this is all very simple script. We just use brute force to crack JSON Web Tokens. Hashcat is highly optimized for GPUs, and it supports a lot of algorithms. So any cryptographic algorithm you can think of, it's supported by Hashcat. So we'll see how long it takes to crack this password. You see that we use 4 GPU devices. This is NVIDIA Tesla P100, pretty performant GPU card. Oh. we have token length exception. Okay, because probably I used the wrong, yeah, I copied that one with non-algorithm, no signature. Okay, this one should be fine. So once again, I could do that cracking on my laptop, and it would take like a couple of minutes. But I decided to use GPU just to show you that the modern hardware is really very performant. And with all those cloud platforms, it's relatively easy to use GPUs for cracking. However, it's not that easy because it took me like a couple of hours to get access to GPU, because usually you have like some quotas for your account, and to increase this quota, it takes time. Okay, so it happened. So we have the password here, the key phrase, obviously JFocus, couldn't be different. And once we know the password, once we know the secret key for HMAC, we can generate another JSON Web Token. With this knowledge, it will be accepted by the server. So we'll try to generate another token. We'll go to this online tool. Okay, as a starting point, I will take my original token. Now we can, set JFocus secret key. And I will change the subject to Lucky 13. So this is my new token. I'm replacing the token with in the browser and refreshing the page. And now I'm POMMAC. Where are you, POMMAC? Oh, very close. That was Lucky 13. So thank you for your cooperation. Okay, so let's move on. This is the performance of hashcat for my laptop. It's like 5 million hashes per second. On those GPU devices, it was like 1.6 billion hashes per second. So it was pretty short password. It was on purpose because we don't have much time to wait for the end of cracking, and obviously the longer password, the length of cracking exponentially grows for brute force. So we usually, as hackers, we would use some masking and some pruning of branches just to speed up the performance. However, in simple cases, brute force is enough. In demo 2, what problems we revealed? Basically, you see that only one token is needed to perform cracking. All cracking is done offline. So no communication with a verification server. So a server or a victim, they do not know that the attack is in progress. So there is no way to recognize it on the server side. Another problem is weak key. Obviously, we should use stronger key for our JSON Web Tokens. But there is more. It's pretty complicated because there are so many algorithms, different kinds of keys, so it requires some knowledge and research from us developers to choose wisely. And so a short summary of available algorithms for JWTs. It's an HS family. It's HMAC, which stands for hash-based message authentication code. And HMAC is available with SHA hashing function. It's a symmetric algorithm which requires a secret key. Another family is it's RS family. It's RSA, asymmetric algorithm with public and private key pair, also with SHA function. And then we have those two families are the most popular, are good enough for most cases. Elliptic curves and probabilistic signature schema are more advanced algorithms, not always supported by all libraries, but they provide stronger cryptographic security. So for HS family, HMAC with SHA, as a rule of thumb, we should use key as long as the length of hash. So for HS, 256 is like 62 bytes, 32 bytes. And there is one more problem with using HS, because it's a symmetric algorithm. HMAC is a symmetric algorithm, requires the same secret key during generation of a token and during verification of a token. What does it mean? It means that when we have a scalable environment with many servers, each server has to possess a private key, right? Because each server performs a verification. So it means that even one server is compromised, the entire system is compromised, because the private key could leak. In case of RS family, it's RSA with SHA. The recommended key size is 2K bits, but if you care about security beyond 2030, you should use 3K bit long keys for your JWTs. And actually, that's the approach I would recommend, because RSA also has a good advantage because it's an asymmetric algorithm. So only authentication servers must store private keys. On the other hand, verification servers can only store public keys. So from the security point of view, we have two zones, separate zones. So it might be better for your scalable environment. Also, you should take into account the longer key, the slower verification. However, if you have a highly sensitive system, the security is much more important than performance. And the performance gain from using a shorter key is not that big. It's just a matter of hundreds of milliseconds, usually on a modern hardware, or less. Okay, so we'll switch to another demo. It's about packet sniffing. Again, I will need your cooperation. But first, I will log in to my server. I will run TCP dump with the script I'm running looks like this. So it runs TCP dump on port 80. Basically, it shows all the content of the requests, and we are grabbing it to find bearer keyword. So I'm running TCP dump, and now my my kind request to you to log in or refresh the page just for me to capture your requests. And oh, so many requests coming and so many tokens to choose from. Okay, that's enough. I need to I need to catch one of it. Okay. This, oh my God, it's okay. Stopping it, because otherwise I wouldn't manage to copy it. Okay, this one. We'll see who is lucky this time. You see that I'm logged in as Patrycja, and after refresh is, oh, cool boy, or call boy. Are you here? I don't see you. Yeah, you are over there. Thank you. How do you pronounce your nickname? Does it mean anything in Swedish? Okay, thank you. So what we've learned here, we've learned that once the token is stolen, it can be used many, many times, right? And the server can't protect against this malicious usage. Yep, it depends on expiration time. Yeah, so that's why expiration times are so important, and you shouldn't set it to a very long values. It should be relatively small. So let's back to the presentation. There was one obvious problem, right? We used HTTP, so lack of encryption. Always in production, to transfer sensitive data, we should use some sort of a secure channel. In case of web application, it's HTTPS. And we shouldn't mix HTTP and HTTPS under the same domain name, because otherwise those tokens could leak. As a funny story, the first version of Gmail, Google is a serious company, but the first version of Gmail used HTTPS only for authentication, and the rest of the traffic was over HTTP, so completely unsecure. Any authentication cookies or tokens could be easily captured by others. So this was an example of token sidejacking. Stolen tokens can be freely used, and the server can't protect against that. They can be used only as long as they are valid. So you see how important it is to set correct, not so long expiration time. And I've seen in many applications that expiration time is like 30 days, so definitely too long. And it was an example of replay attack. And now we will move to the last demo. We know that HTTP is bad, so we can switch to HTTPS. And even though we will be using HTTPS, I will still manage to steal one of your tokens. And I will use HSS Crosssite scripting to steal a token. Okay, so I will relog to my account. Yep, nice. Who managed to do that? Over there. Nice capture. It was it was a hidden bug, weak password. It was, oops, sorry. Sorry. I'm switching. Yeah, defeated. Yeah, and it was on purpose. I didn't tell you, but yeah, there was a hidden sort of a bug because I used a weak password on my account. During DevOps, I used password. This time, I used like, it was 1Q2W3E, so pretty common pattern on a keyboard. So congratulations, you have very smart audience. I'm impressed. Okay, but I will update this homepage. I will update with prepared attack vector. I will try to inject some JavaScript here. If you take a look at the code, it's just sending token. It gets a token from a session storage and sends it to some evil server. And then it shows the alert that your token has been stolen. Okay, so what happens here? I will update it. So now when you click in my nickname, or actually my first name, this JavaScript code will be executed. So I will need your cooperation. Please click, and I will observe on my server, this time evil server, I will observe logs and see, oh, again, so many tokens coming in. Yeah, those are stolen JWTs. And now I will copy one of them. And we'll see who is lucky. Lina. Where are you, Lina? Oh, over there. Thank you. So you see, this time, OK, it was not automatically executed JavaScript. A user, a victim, needs to actively click the link, but still it's relatively simple kind of attack and relatively approachable. The attack vector was very simple. The only trick was to load the link URL with stolen cookie into image source. Why? Because browsers have something what is called same origin policy. So they are not allowed to connect to another domain name. It's only available for images, scripts, the fonts, that kind of stuff. So they can download images from a different domain name than the application is served from. So to avoid and bypass the same origin policy, we used image source, and this way we could be able to send token to our evil server. The problem here is that we have XSS. That's obvious. On the other hand, there is no way to block access to a session storage for JavaScript. For cookies, we have a way. We have like HTTP only flag, we have secure flag, we have same site flag. So we have a set of flags which improve security of cookies. HTTP only means that this flag can be accessed by JavaScript. It can be only sent over HTTP. So for session storage, we don't have any such mechanism, so we can't protect. So to be safe with JSON Web Tokens, we can use a different transport and storage mechanism. Even though we use JSON Web Tokens, we can still use them in cookies. Those cookies won't be stateful. It will be a stateless cookie because there will be no server-side session. So in terms of best practices to protect against XSS, we should use content security policy, and in our case it would help because content security policy provides a set of rules what is available for a given application or downloaded from a given domain name. So for example, which other domains it can connect to. Or from, for example, we could restrict that images are downloaded only from the same site. So in that case, our bypass wouldn't work. Obviously, we need some code audits, pen testing to discover XSS, and good libraries that support anti-access rules and properly escape content. Another solution is hardened cookie as a storage mechanism for JWT. We don't have any server-side state, and we can use flags to improve security of such cookies, like secure, HTTP only, same site. HTTP only is one of the most important one here. The funny thing is that HTTP only flag was introduced first in Internet Explorer. The browser perceived as one of the least secure browsers. But they were working to improve their security. But with cookies, we have another problem because we end up with a possibility of CSRF, cross-site request forgery. But that's something for another talk, I think. To avoid token sidejacking, once a token is leaked, anyone can use it. So to avoid it, OWASP, which stands for OWASP, Open Web Application Security Project. It's a non-for-profit organization that aims in increasing security awareness among developers. It's OWASP.org is the site you should have known, and if you don't, go and check out their resources. They have a lot of good materials about security. So they propose a solution to token sidejacking. It's like fingerprinting. The scenario is that we use both JSON Web Token and a cookie. In JSON Web Token, we include extra claim. It's called like a fingerprint claim. It's a hash random value. A raw random value we include in a cookie content. And during verification phase, a client should send both a token and a cookie. And the server obviously verifies JSON Web Token itself, but also verifies whether hashed cookie value is equal to a fingerprinting claim in a token. How it helps? Because if a hacker can easily steal, for example, JSON Web Tokens, but it's much more difficult to steal a cookie. So, and in such a case, a hacker can't use stolen cookie because the server will notice lack of, can use a stolen JSON Web Token, and the server won't verify it successfully because there will be no cookie available. Please note that that random value is hashed in a token because from the hash it's very difficult to restore the original value. So for hackers, it would be very difficult to restore it. So the hacker can't prepare that cookie with a random value, secure random value. Okay, I'm sorry. Just a few last sentences about basic hygiene with JWTs. Remember about logouts, that's difficult because there is no built-in feature to revoke a token. And from the security point of view, user should be able to explicitly stop a session. The similar problem is with timeouts, no built-in feature to implement inactivity timeout. So to avoid relogging, often we use long expiration time, but as I said to you before, it's dangerous because it, due to this, we have a very long time frame for attacks, possible attacks. So in case of logouts, again, on the server side, we need to store something, some sort of a blacklisting, invalidation store. So unfortunately, the state strikes back in that case. For timeouts, we can use like shorter token expiration times, accepting relogging, or refreshing access token. So some of those solutions. So it's only the tip of an iceberg when it comes to security in general. But remember, a fool with a tool is only a fool, so we as developers can't be fools. We need to know what we are doing, which tool is right for us, and how to use it wisely. Nobody's perfect. We all make mistakes, but all we can do is to improve ourselves as developers. So continuous learning and good luck with your security with JSON Web Tokens. Thank you very much.